everyone, it's Judy Warner. Welcome back to this week's Ecosystem Podcast. Today I'm joined by none other than Lee Ritchey, President of Speeding Edge Solutions and High Speed Digital Experts. We're going to talk about Skew today and ways that you can avoid or mitigate it in your designs. And we also talk about the future outlook across the industry to solve this problem long term. Before I jump into this conversation, I wanted to give a shout out to Christopher Jackson, who reached out to Lee and I through YouTube and asked us to do this podcast. We always love hearing from people like you and Christopher to give us ideas for guests and topics. So, Christopher, hope you enjoy this one. Now let's jump right into our conversation with Lee Ritchey of Speeding Edge Solutions. Hi, Lee. It's so good to see you, my friend. We haven't done this in a while, and I'm really excited to have you on today.
Well, I'm excited to do the same thing. It's always been fun to do this because you're pretty good at prying out information that needs to be recorded, and I think that's what we're going to do with this session.
We are indeed. Get ready, buddy. I'm going to hold your feet to the fire. So
Right.
today we're going to talk about something we've talked about in the past, but as you know, nothing stays still in this industry. So I wanted to get you on and talk about Skew. But before we do that, for the two people in the industry that might not know who you are, why don't you give us a brief introduction?
All right. My name is Lee Ritchey. I'm president of Speeding Edge, which is a consulting and training company. I've been in a high-speed business since it started with ECL long ago, and have spent pretty much all of my career doing pushing the envelope, going up and up and up in speed. And in the early 70s, when we were doing high-speed computing, we were delighted that we got our supercomputer to clock speed all the way to 33 megahertz. That's unbelievable that it was that slow, but that semiconductors were that slow, if you want to call it that. At any rate, from that experience, I've spent all my career on startups who are always pushing the envelope with the next new product. And for the last, since the mid-90s, it's been internet products primarily. And to give some insight into what we have done since in 1996, we were struggling to make all of our links run error-free at 10 megabits per second. 2 years ago, I worked on an interface to undersea cables, to get the bandwidth up in the cables, where the data rate was 400 gigabits per second. Gigabits per second. That's a 40,000 to 1 change in bandwidth in a little over 20 years. And so that's how rapid our industry has changed, and it has everything to do with the classes I teach, because engineers have got to get up to speed at almost makes your nose bleed. And so part of what, differential signaling is what has allowed us to do that, and that's going to be what we talk about here. And I'm currently working on new laminates to deal with the next round, whatever the next speed increase is. Who knows where we end up? I thought 5 years ago we would never get to 100 megabits per second.
Yeah.
Got that one wrong.
Yeah.
That one went by just like that.
Well, to your point, it just blew my mind. I think because we all got in a time warp during COVID. Before COVID, I had done a podcast with Jason Ellison, and I think it was Jason. We were talking about doing, getting to 112, and I'm like, no, we're not. And so I just sort of was busy and wasn't paying explicit attention to high speed. And then I come back, Samtech starts talking about 224. And I'm like, what? You mean you hit 112 and now you're shooting for 224? Like, It felt like Rip Van Winkle. What just happened? So these are crazy times. So let's talk about, why don't you give us a quick, for our listeners, just give us I'm sure everyone knows, but give us a quick definition of skew, and in the case of diff pairs, what causes it and the problems it causes.
All right. Well, the internet as we know it and high-speed signaling as we know it is possible because of differential signaling. And basically what we have is two equal and opposite signal waveforms that are launched from a driver down a transmission line, which is two transmission lines really, and arrive at a receiver that looks at the difference voltage. That's where the differential comes from. It decides is this a 1 or a 0. Well, how successful that is done depends on the two signals arriving at the same time. And when we decide, we have a logic state change is when the two waveforms cross. If they don't cross in the middle of the waveform, in other words, if they misalign, the bit error rate goes up, and at some point the link will not work because they don't arrive. They're so far apart when they arrive that the link fails, and that's what we call skew. Skew is misalignment of the two signals at the receiver, and the primary cause of that is a difference in travel time across a printed circuit board. And of course, printed circuit boards are made from a combination of resin and woven cloth, glass cloth. And those two have very different dielectric constants. So if one member of the transmission line is in the resin, it's got a dielectric constant around 3, and the other one's on glass, whose dielectric constant around 6. The speeds are going to be substantially different. And so that is basically the only real cause of skew in modern printed circuit boards. We've got everything else that is involved so well made that it's basically the glass we require to make a laminate dimensionally stable that is the villain.
Right. And so, and usually that's in the form of a grid, right? Those it's woven glass.
It's woven cloth, right? Just like linen, just like any woven cloth. And in fact, the materials are woven on the same looms that used to make cloth. I went through a weaver in North Carolina, and it was in an old textile mill that was once upon a time making calico or something like that. And you could see all around all the stuff from making cloth. And so, same technology.
Right. Ancient technology, but it works, right? So, because of this issue that's well known and is problematic, tell us a little bit about how engineers are handling that today. And then I know this is a problem you've been looking at, solving, working through for a very long time because of your expertise and focus on high speeds. So kind of give us a sense of where we are today and how engineers are dealing with this today with high-speed electronics.
All right. Well, there are two techniques being used. One of them is to route the traces in the artwork, X and Y, and then when we put the artwork down on the panel and printed circuit board, we tilt it at an angle so that they're not traveling straight down one fiber in between the two fibers. And that's the dominant solution that's being used. And early on, the number was used as a 15-degree angle, and that turned out not to be good enough. And later on, research was done and was discovered that at 5 degrees, that pretty well takes care of it. So a very large part of the industry is doing it that way. The disadvantage of that is boards are rectangles, and so are the fabrication panels. So
Yeah.
if you cock the artwork at an angle, you waste a lot of material,
Yep.
or it may not fit. For example, we build a lot of what we call pizza box boards, which are one U rack mounted,
Mm-hmm.
and that's the dominant board in this whole industry.
Right.
And that's wide enough that you almost can't do that, caulking on the panel and
Right.
make it fit.
Yeah.
And so that's not my solution.
Yeah.
My solution is there are probably a dozen different weave styles that you can choose from for these thin laminates. And the classic's always been what's called 106 glass and 1080 glass, and that was the first place that this problem cropped up because 1080 was automatically how you made a 4 mil core. That's where this problem first popped up. Well, we discovered there was something called spread glass, and the fibers in each glass bundle were spread out so that you had a uniform surface of glass, and that solved the problem. And for quite a long time, we were using a material called 3313. That's a glass weave. And we built all kinds of boards with that at a fabricator up in Oregon and had no skew. And so we thought, oh, that's the wonderful material. And so the test boards we did for Isola, we made from 3313, and they all failed skew. Every one of them failed. What's
What?
going on here? Turned out it was a different weaver.
Oh, no. So it's where they were sourcing the
yes,
glass.
and so we got to digging into it, and the reason that the glass is being spread is not signal integrity. It was for drilling laser drilled blind vias, because if the glass was not uniformly spread, if the beam intensity was high enough to burn through the glass fibers where there were none, you got a huge erosion, and the holes were basically so badly formed that you couldn't plate them. And so that's why glass got spread. And of course, the driver for that was cell phones, because they're all the build-up technology. And of course, the spreading that was being done in these two variations of 3313 I talked about, they were happy with that. That spreading was okay. It was good enough for a laser drill blind via,
I see.
but not good enough for skew. And so we spent, I don't know how many hours trying to get the IPC standard for how glass weave is specified to get a definition of spreading that was good enough so we could trust and get the same thing from everybody. But it was very much like herding cats. The committee had a member from pretty much every glass weaver on it, and they would not share how they did spreading.
And there is the issue.
There's the issue. And so out of frustration, I finally just quit trying to get that done. And so we searched around for a better solution, and this is it. There is a spread glass weave called 1067, which is intended for the same application. And we discovered that if you just use one layer of that above and one below your transmission line in one direction, you still get skew. So we discovered by building test boards that if I put two flies of 1067 above the transmission line and two below, we got it. And
Now, did you do those in different directions when you layered them like that, Lee?
No, you really can't
Same
do
direction.
that.
Okay.
Because of the way the weave is made. I mean, that would be one solution, but
It'd be bad for the board.
if you look at how laminate is made, you're going to wind up throwing away a lot of material if you do that.
Yeah. Okay. I wasn't sure what that would do.
Yeah.
So in this 1067 and doing the stack, okay, I have two questions. One, when you do spread glass, you mentioned about the different loss of the glass versus the laminate. What does that do to your loss?
Well, so we're really talking about the loss in the resin versus the loss in the cloth, I
Yes.
think. Well, we didn't see a significant difference in loss when we had Skew. I think that's your question. Do we also get more loss when we have traveling over the glass bundle versus
Yes.
in the dielectric? And the answer is yes, but the number is pretty small. The difference is pretty small. And the reason for that is the manufacturers of these systems that are aimed at this market have successfully reduced the loss in both materials so low that any difference you would see is second or third order.
Okay. All right. That's good to know. And then in regards to this 1067 glass and putting two layers above and below the transmission lines, is this something like, did you publish that? Like, is that something known to engineers? Can they tell it from data sheets if they wanted to implement it?
Well, I've taught that technique in my classes for the last 7 or 8 years.
Mm-hmm.
So it's in the public domain.
Okay.
I mean, I suppose that John and I could have patented that, but we've been interfered with by too many patents in the past, and so we don't want to constrain the problem.
Right.
That way.
Yeah, I understand. Well, maybe we can. Yeah, well, maybe we'll go dig those out. I'm just thinking that people listening to this might want to be, oh, yeah, I want to do that. So I want to send them somewhere else where they could maybe access things that are in the public domain. That's why I was asking. Okay, so spread glass is the best solution, and to do it in this way. Now, it sounds to me from talking to you and Kella that there's a fundamental limit of laminates and speeds somewhere around 56 gigabits per second. Can you talk about that a bit? And again, how do we deal with that? As you mentioned in the beginning, like the speeds aren't going to slow down. Bandwidths are not going to slow down. So we've sort of created a stopgap. That's good. And where do we go from here, Lee?
Well, so the solutions that I was describing and the designs I was describing were 32 gigabits per second.
Okay.
And at 56, even that solution doesn't work. And so, because there's not much room for error at that data rate, at 56 gigabits per second, a bit period is 20 picoseconds.
Mm-hmm.
And so 5 picoseconds of skew does that in. Well, we had as much as 5 picoseconds with that solution I just talked about at 32 gigabits. That's okay. So what we're doing right now is flyover, meaning that we don't have the transmission lines in the board. They're in twin X that's outside the board.
Okay.
And no surprise, that's a very expensive solution.
Right.
And so, as it turns out, right now, the only signals that run at that data rate are between the fiber interface, the SFP module, and the first integrated circuit. So you'll see that from the front panel back to the first integrated circuit that receives that data rate, that's a flyover connection. And from there on, everything in the board is at 32 gigabits per second.
I see. So they just use it where they need it and
Yeah,
keep the other transmission line on the board.
and you just hinted at earlier about 112,
Yeah.
and so if there is 112 in that path I just described, and you saw at DesignCon this year trying to do 224.
Yeah. Yeah, my friends at Samtech, I never did get over to their booth at DesignCon. I wanted to, but I was just too busy podcasting. But what did you see over there? And I know it was just a kind of proof of concept, dreamy land at this point. There's a whole ecosystem and a lot of problems have to get solved before then. But what were your
No big surprise.
observations?
All the connections were twin X flyover.
I see.
Where I was actually going with my last little bit is, if I take that last inch, if you want to call it, at 224, down on the board, I'm going to have to double the data rate in the board, and that's going to be 56 gigabits per second.
I see.
And now we're stuck. Because there isn't any material right now that will, assuming you don't have a loss problem, there's no material that is good enough with respect to skew.
I see.
To go at that data rate.
Got it. So now what, Lee? I mean, we got the flyover cables, but now what? Where do you imagine we're going to go? And we're always talking about, and I really don't know enough about it, but I imagine you do, optics or embedding things in the board. Like, is there any solution that gives us some hope, I guess?
Optics is more expensive than twin X.
Yeah.
By another order of magnitude. I mean, people talk about optical connections in the board, and that is not realistic. What we need to do, and I'm working with two suppliers right now, we need to make a material that does not depend on glass.
Okay.
Because that's the villain. And if you reflect way back, the reason there's glass cloth is that produced the mechanical stability for a 2-layer board.
Yeah.
Or a 4-layer board. Well, when we're talking about this kind of a design, it's rarely under 20 layers.
Yeah, exactly.
Of which probably half are copper planes. And the copper planes are now producing the dimensional stability. We don't need the glass anymore for that.
Oh, interesting.
Because the copper sets the temperature coefficient of expansion of the whole thing, not the glass.
Okay.
And so I'm working with two suppliers to come up with a laminate that does not include glass.
Okay.
We're not there yet, but that's what we're doing.
So will you, I assume that as part of that, and I know you can't divulge who those laminate suppliers are because you're under NDA, but what are you going to make test boards, and how far along in the process are you on that?
Yes. We have already built some test boards.
Okay.
At the moment, they're not satisfying the UL requirement for multiple reflows.
Okay.
And so that's the problem is being worked right now. I mean, the multiple reflow thing really is for avionics, where you might have your airplane sitting on the desert in Arizona inside the instrument's 150 degrees.
Yeah.
Half an hour later, you're at 30,000 feet where it's 60 below. And you do that over and over and over again. The printed circuit board gets cycled. And that's the reason for that 20 reflow business. We don't need that. In a server farm, it doesn't go on and off. So we don't need that, but to get certified, you got to do that for material.
Oh, the blessing and curse of standards,
Yeah. Yeah.
right?
Well,
And it's,
and
yeah.
there's another irony, and that is when we're building we built all these test boards in 2013. Is that right? Yeah, 2013. The company we were doing it for had two laminates that had no skew, and we were delighted with those and wanted them to commercialize the material. And for a reason we don't understand, they didn't do it. But now 10 years ago, we had material that satisfied the problem, but the manufacturer chose not to commercialize it. Don't know
Woe
why.
is me.
Yeah, yeah.
Did that back in 2013 involve glass? And would
They
it meet the 56 gig ceiling you're talking about?
wouldn't tell me what was in the material,
Okay, makes sense.
but yes,
Patented.
it would do the job at 56 because the loss was low enough. It would have done the job.
Let's go beat 'em up, Lee.
I wouldn't be surprised that they lost the recipe. The
Oh.
company had some severe reorganizations.
Mm-hmm.
In fact, the guy who was developing that material is one of the people who's developing the material we're testing right now.
Okay. Well, keep going, Lee. Keep fighting the good fight.
Yeah.
We appreciate you doing it. This is really interesting conversation, and since last time we talked about it, you have some interesting additions that I didn't know about. If you were a high speed engineer today, where would you go look besides some of the things in the public domain that I'll try to hunt down for our audience? Where can they go to do better? Maybe they're not all the way, at 56, but maybe they are at 32. And where can they go to learn more and maybe learn some techniques to help them with their skew problems?
Well, the dominant place that topics are explored
Mm-hmm.
is DesignCon.
Okay.
All of the things we're talking about have been presented as papers at DesignCon
Okay.
and are available online from DesignCon.
Okay.
I'm not sure if I'm not sure how you get access to those.
Okay, well,
Because,
I have a relationship with the Design Con folks. So for our audience, I will go try to hunt that down for you. And whatever I find, I promise I will put in the show notes for you, whatever I can find. And Lee, I know you have just some, great classic books out on high speed. Where would you like our listeners to go to tap into some of your hard-won wisdom that you've published over the years?
well, we have two books. They're ebooks now. We self-published, and the reason we did that is we wanted color, and none of the technical book publishers want to do that.
Yeah,
So
which is
we
funny.
self-published, and it was not a cheap enterprise to do that.
Mm-hmm.
Funny thing about when you go to a printer and say, I want 3,000 of these books, and says, okay, here's the start button on the press, but before I'll push it, I want a check for $50,000.
Yeah.
Yeah, and it kind of sets you back a little bit when you write that check. Say, boy, I hope somebody buys these books.
Yeah, right.
They did, but we don't want to do any more $50,000 checks. So they're ebooks, and they're on our website.
Okay.
And anyone who wants to can go on there and buy an e-copy for $25. And the
Which is
first
a heck of a
volume,
bargain. Yeah.
yeah, it is. If you think about what the prices of books you buy from somebody like Prentice Hall.
Yeah.
Anyway, the first volume is what I would call the fundamentals.
Mm-hmm.
The second one is where all this stuff is we just got talked about, the high-end stuff.
Okay.
And volume 2 is now a textbook at my university, which is kind of nice.
Yeah.
And nice to know you did something that a professor wants to use.
And passing on the baton. Like I said, this is hard-won wisdom. You got the bumps and bruises to account for it. So
Yeah.
that's great news.
Yeah, from probably about 4,000 or 5,000 designs.
Yeah,
At
just a
least
few.
that many. At least that many. Yeah.
Yeah.
Yeah. And pushing the envelope every day.
Yeah. Well, keep carrying on, Mr. Lee
Yeah.
Ritchie. We need you. Just keep doing it because,
Okay.
there's a few out there trying to solve these problems, but I really appreciate you because you have your feet on the ground working with industry and engineers to really solve these problems. So we appreciate you very much. And thanks so much for coming on and talking to us today and getting us up to speed.
Okay, there's one other thing I should point out.
Okay.
We should have written a volume 3, but the first 2 are hard enough work. We chose not to do that again. And on my website is a digital library, which is all kinds of articles I've written since then that are my volume 3. And you can buy
Okay.
that. You can buy that library.
Okay. I'm glad you inserted that. So again, for listeners, I'm going to put all those links below for you so you can go tap in and learn much more in much more depth than we've had the opportunity to talk about. But Lee, thanks again. I appreciate you. And thanks for coming on today and sharing with engineers how to navigate this pervasive problem, particularly in high speed. I hope you'll come back and tell us when you make more progress with those laminate manufacturers.
All right. You can bet we'll make a lot of noise when it's real.
Okay.
All
All
right.
right. Well, don't forget us. We'll help you make a lot of noise.
Okay. My pleasure. Thanks, Judy.
Thank you so much. For our listeners, thanks so much for joining Lee Ritchie and I to talk about the problem in a skew and the ways you can manage it and tap into more resources. We will see you next week. And don't forget, we're going to be at IMS the second week of June. And so I hope you'll stop by and see me at booth 1855. We'll see you next week. Until then, remember to always stay connected to the ecosystem.